Hello. In this video, I'm going to be explaining problem 9 from the F equals MA 2018 contest version A. So in this problem, we have a mass that is originally on a horizontal surface and that is pulled upward by a force from one side. And we are asked to find the normal force, or at least a bound for the normal force, on the block at the moment that the right end of the stick is just leaving the surface. So the key in this problem is to look at two things, both force and torque. We need to look at forces because we need to know when the block will be able to leave the ground, but we also need to look at torques because we know that one side is going to be fixed. Or that is the point that is on the left side is actually going to be basically a pivot point for when the block starts rotating. So basically, you have a pivot point, so this is mass m, so we know that there's going to be a force mg acting on the center of mass. Of course, the gravitational force is actually acting everywhere, but effectively, you treat it as a gravitational force acting at the center of mass. Then we have a force acting upward on the right side, and then this is just as the block is just as right side is leaving the surface. And then we also have a normal force N, which is only acting on the left side, because remember, this right side is actually just leaving the ground, which means that the normal force can no longer act on it. So the normal force can only act on the left end point, because the rest of it will be raised ever so slightly. Now, for convenience, let's say that this block has length L. Ultimately, this won't really matter because, as you might be able to predict, all the L's will eventually cancel out of any equations that they show up in. But now we can set things up. So we can look at the total torque first. So let's say our pivot point is P. So the torque around point P is equal to the force F times L, then minus mg times L over 2, and then the normal force does not contribute any torque because it's acting at the pivot point. And now we have our net force, which will become F plus N, those are the two upward forces, minus mg, which is the downward force. So now, how are we going to relate these? Well, basically, the first thing, so what we need to do is to look at how quickly the block will begin to rotate. So what will happen is that the center of mass will have a certain acceleration, and that acceleration will be tied to the angular acceleration of the block. And so the torque about the point will be the moment of inertia around the point times the angular acceleration alpha, and then that force is going to be equal to the total mass times the acceleration of the center of mass. Now, these two quantities are related. How are they related? So the angular acceleration alpha is just going to be equal to the acceleration of the center of mass divided by the distance of the center of mass to the pivot point, and so that will be equal to L over 2. So it will equal 2 times ACM over L. And so we also know that the moment of inertia around the pivot point is equal to 1/3 times mL squared. This is a formula that is worth memorizing. There are some basic moment of inertia formulas that you should probably just know by heart. And the moment of inertia of a rod about one of its endpoints for an axis that is, perpendicular to the rod is definitely one of them. So these are ones that we're just going to cite. And so now, if we write out the torque equation, we'll see F times L minus mg times L over 2 is 1/3 ml squared times acceleration of the center of mass, and then times 2 over L. So so that term in parentheses is alpha. And now we're going to get some cancellation, so this L squared will cancel with L to just make L. And then also, we're going to, now every term actually has a term of exactly 1 power of L, so that goes away. So let's just rewrite it to make it a little cleaner. F minus mg over 2 equals 2/3 m times the acceleration of the center of mass. Okay, and now what we have is that we can actually plug this in to the let me rewrite that. So we have F equals 2/3 m times the acceleration of the center of mass plus mg over 2, and now we'll plug in our expression for F into this other equation. So let me start a new page right here. So again, we have, let's look at this, F plus n minus mg equal to m times the acceleration of the center of mass, but we also have F, which equals, from what we just proved, 2/3 m times the acceleration of the center of mass plus mg over 2. And so now we write that out, and what we will get is m, and we see plus mg over 2 minus mg, so that's m minus mg over 2 equals, move the 2/3 to the other side, so we get 1/3 m times the acceleration of the center of mass, we get n equals mg over 2 plus 1/3 m times the acceleration of the center of mass. Now we see that the acceleration of the center of mass is greater than 0. And so what we know is that n is greater than mg over 2. However, so now let's look back at our options. And let us see what we have. Well, and we see that the right option, we can also see, don't need that. We can also see, without too much trouble, that the normal force also has to be less than m times g. And so what we end up getting is that the correct answer is right here. mg greater than n greater than mg over 2. Alright, and that concludes this problem, and I hope that was helpful. Thank you for watching.